Have you ever stopped to think about the absolute mountains of data that run our world? I mean, everything from your social media feed to your last online purchase, it all depends on databases running smoothly behind the scenes. Well, today, we're going to pull back the curtain on the secret sauce that keeps all that data from turning into chaos. Database normalization. Let's demystify it. But hey, before we can really appreciate the cure, we have to understand the disease, right? And the disease almost always starts with messy, disorganized data. It might look simple on the surface, but it's often a ticking time bomb. Okay, so take a look at this. This is a table we'll call Employee 2. Seems pretty harmless, doesn't it? You've got employees, departments, salaries, the courses they've taken. But trust me, this simple-looking table is absolutely riddled with hidden traps that can seriously mess up your data. And these traps in the database world are called data anomalies. You can think of them like nasty little gremlins that pop up and cause chaos whenever you try to do something simple, like insert, delete, or update information. Let's see what kind of trouble they can cause. First up, the deletion anomaly. And to see it in action, let's just ask a simple question. Let's say Alan Beaton leaves the company. What happens when we delete his record from the stable? So we delete that row. Easy enough, right? Nope. Look what happens. When Alan Beaton's record goes, we don't just lose information about him. We completely wipe out the only record we have that the tax accounting course even exists. Poof, it's gone. That is a massive problem. Okay, so that's deleting. What about adding new people? Well, that's a mess too. Meet the insertion anomaly. See, we hire a new employee, but they haven't taken a training course yet. With this table, you literally can't add them. The structure blocks you from entering perfectly good employee data just because another piece of info is missing. And finally, this one is a real headache, the modification anomaly. So Margaret Simpson, employee 100, gets a well-deserved raise. Great for her. But for us, to update her salary, we have to hunt down every single row where her name appears and change it. If you miss just one, and it's easy to do, your data is now inconsistent. It's inefficient in just asking for errors. Okay, so we've got data disappearing, we can't add new info, and we're scared to update anything. It's a disaster. But don't worry, there's a really elegant solution to all of this. It's time to meet the hero of our story, normalization. So, what exactly is normalization? Well, you can think of it as a formal recipe, a step-by-step process for taking these big, messy, problem-filled tables and strategically breaking them down into smaller, much more logical and stable tables. The whole point is to get rid of that duplication and fix those anomalies for good. And this visual? It sums up the whole idea perfectly. We start with data chaos, one big clunky table. And through a series of steps, which we call normal forms, we transform that chaos into organized clarity, a set of smaller, neatly interconnected tables that actually make sense. All right, you ready? Let's get our hands dirty and walk through the process. The first, most basic stop on our journey is called first normal form, or, as you'll usually hear it, 1NF. The rule for 1NF is about as simple as it gets. Every single cell in your table can only hold one single, indivisible piece of information. That's it. Think of it this way. You can't stuff multiple items into one box. No lists, no comma-separated values, just one thing per cell. We call this being atomic. Here's a textbook example. See that top table? The contact numbers cell is a total mess. It's got two different numbers crammed into one spot. To get this into first normal form, we just break them apart. Give each piece of information its own row. See? Simple, clean, and atomic. Okay, so all our data is atomic now. We're officially in 1NF. What's next? Well, we move on to second normal form, or 2NF. And this is where we really start to attack that problem of data being repeated all over the place. So for a table to be in 2NF, it has to meet two conditions. First, it's got to be in 1NF. That's a given. The second rule is about the primary key, the column that makes each row unique. The rule is this. Every other column in the row must depend on the entire primary key, not just a part of it. This gets rid of what we call partial dependency. Let's go back to our problem table, employee 2. Now, the primary key here is actually a combination of two things, the employee ID and the course title. But think about it. Does an employee's name or their salary have anything to do with the course they took? Of course not. That information depends only on their employee ID. That right there is a classic partial dependency, and it's the very reason we had that modification anomaly with Margaret Simpson. So, how do we fix it? You guessed it, we split the table. We create one neat table just for employee information, with the employee ID as the key. Then we make a second table that does one job and one job only. It tracks course completions. Just like that, the partial dependency is gone, and Margaret's salary now exists in only one place. We're making real progress. The partial dependencies are gone, but there's one more kind of subtle problem we need to fix. And this brings us to the final stage we'll cover today, third normal form, or 3NF. You know the drill by now. To be in 3NF, a table must first be in 2NF. Then, we add one more rule. You can't have a non-key column depending on another non-key column. It creates this weird indirect chain reaction in your data, and it's called a transitive dependency.
This little diagram makes it crystal clear. The primary key, employee ID, determines the department ID. That makes sense. But then, the department ID, which is not the key, determines the department name. See that little two-step process? That indirect hop from employee ID to department name through department ID? That is a transitive dependency.
And by now, I bet you can guess the solution. We break the chain. We split the table one more time. We create a whole new table just for departments, with department ID as its key. Now the employee table just needs to hold the department ID to create the link. With this change, every single piece of data in that table depends only on the key, the whole key, and nothing but the key. So let's take a quick breath. We've gone on a journey from 1NF all the way to 3NF. We've been breaking down our table, creating these clean relationships. But let's ask the big question. What's the point? Why did we go through all this trouble? This flowchart right here is the perfect summary. We started with a total mess, an unnormalized table. In 1F, we made the data atomic. In 2NF, we eliminated those partial dependencies. And in 3NF, we got rid of the transitive dependencies. Each step brought more structure, more order, and more integrity to our data. And here it is. This is the payoff. By normalizing your database, you absolutely minimize data redundancy. You prevent those nasty insert, update, and delete anomalies we saw at the start. You improve your data integrity, which means you can actually trust your data. And ultimately, you make the entire database dramatically simpler and safer to work with. This isn't just theory. It is the foundation of almost every single reliable application you use. We've seen how normalization leads to this beautiful, logical, and consistent database. It sounds perfect, right? But that leaves us with one last, interesting question to chew on. In situations where all you care about is the absolute fastest possible result you can get, is a perfectly organized database always the right choice? We'll leave you to think about that one.